All right. Now have a look at page 25, March 2018, P42. This one is actually your binding energy curve, binding energy per nucleon curve, right? So here they mentioned to you that one particular fission reaction can be represented by this given equation here. The variation with nucleon number A of the binding energy per nucleon BE is shown in this figure here. On this figure, mark on the line the position of the following three nucleus. Okay, the first one is uranium-235, label this point U. Second one is barium-141, label this BA. And the last one is krypton-92, label this point KR. So here, just now as I mentioned to you, look at where the peak is. The peak is somewhere around here, right? This one is by right going to be 56. It belongs to ferrum 56. So then from there, if you're talking about uranium-235, uranium-235 probably will be around here, where you have 235 here. Okay, this one label it as U, and then you have barium-141. So barium-141 probably would be somewhere around here. This one is 141. This is BA. And then the last one is krypton. Krypton is 92. So it's probably somewhere around here. Okay, so this is KR. Okay, so this is one example of why you need to know the binding energy curve. Then is there any questions from here? Nope, there isn't. This is just one example. Okay, if you're okay with that, then maybe we look at page 20. Okay, have a look at page 20. All right, just have a look at it while I open up the past year question answer. This is June 17, P42. Nuclear physics question in paper 4 is almost always going to be the last part of your paper, usually question 12 or question 11 or 10. Okay, right, now in your case here, you have one nuclear reaction that can take place in a nuclear reactor that can be represented in part by the following equation. Data for nucleus and some of these particles are given here. From here, they want you to complete the nuclear reaction shown above. Okay, so in your case, this one is something that you will have learned in your AS particle physics. You will need to apply conservation of proton number and nucleon number, which basically just means this lah. Proton number before the reaction is equals to proton number after the reaction. The same can also be said for nucleon number lah. Nucleon number before the reaction is equals to nucleon number. Sorry, let me rewrite this. Nucleon number after the reaction. This is what conservation of proton number and nucleon number mean. Okay, so in your case, let's just zoom in a little to this equation. Okay, so here you just try to apply the conservation of your proton number and nucleon number. Now in your case, you look at your nucleon number, sorry, proton number. This one is just going to be 92. Okay, so all in all, when you go and look at after the reaction, it should also be 92. But you see here, this is 42, this is 57. So 42 plus with 57 is already 99 here, right? This one in itself is already 99. Then this one is 0. So is 92 equals to 42 plus with 57 plus the unknown element here. Let's just call this your proton number Z. Okay, proton number Z. So Z here would be 92 minus 42 plus minus 57. Notice that there's a -7 here. The proton number here should be -7, okay? But here you'll notice that only beta minus or electron has negative proton number. Therefore, is 7 electrons, okay? Only electron would have a negative proton number, so you know already this is talking about electron, okay? And in your case, you must have 7. Okay, so it's 7 electron here. Now you can also likewise check with your nuclear number to see whether you did it correctly. This one will give you 236. So with what you have now, if you try to add up your nuclear number after the reaction, it will be 95 plus 139 plus 2 plus 0. It will be 236 exactly. Okay, so this is the correct answer. You would have 7 electrons. Okay, 7e -10. All right. Now, in part B1, show that the energy equivalent to 1 U is 934 mega eV. Show that this amount of mass has an energy equivalent to 934 mega eV. So this one, we already went through it in the notes just now. When it comes to energy changes caused by mass changes, you will always use E equals to delta mc squared. In your case, your delta m is actually U, okay? So it's UC squared, sum in the value of U from your data sheet, multiply with your speed of light, square it, you're gonna get this answer here. 1.494 times 10 power minus 10 joules. This is in joules. You want to convert it to EV, you just divide. No? So in general, this is the working. You convert from EV to joules, you multiply with 1.6 times 10 power minus 19. But if you want to convert from joules to EV, you divide by 1.6 times 10 power minus 19. Which is what you're doing here. So do this division, you will get it as 934 times 10 power 6. You specifically want to isolate out 10 power 6 because you want to write it in terms of mega. You want to have a prefix of mega. So eventually you get 934 mega eV, just like that. Okay, so far so good. All right, then after that, let me just erase off whatever is unnecessary here. Then from there, okay, maybe it's better I just clear off everything. Okay, now from there, calculate the binding energy per nucleon in mega eV of lanthanum 139. Okay, so in your case, they want the binding energy per nucleon. All right. In general, if you want to find, if you're talking about binding energy is energy required to separate a nucleus into individual nucleons to infinity. That's the definition of binding energy. Okay, so in your case, think of it this way. Your lanthanum 139 57, it has 57 protons, and then you subsequently have 82 neutrons. Okay, so you're talking about the nucleus itself. You have 57 protons and 82 neutrons here. So you want to separate it into the individual nucleons. So you can probably think of it as this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this one also something similar. Okay, so this one here, you needed to separate it into a total of 57 protons. And then after that, you have to separate it into 82 neutrons too. So when you go from here to here, you need energy to break it apart. You need to supply energy to break the nucleus apart into the individual nucleons. And then once you supply the energy, that energy gets converted into masses, which in turn then causes some sort of mass increase. There's actually a mass defect here. Okay, so that time I mentioned that you go from here to here, you have mass gain, right? All right, you have a mass defect here, a difference in mass between your nucleus and your nucleons. So the energy that you use to separate your nucleus into the individual nucleons is actually your binding energy. Okay, going from left to right is actually your BE. Okay, so whatever energy you supply to separate your nucleus into your individual nucleons is actually your binding energy. Okay, and this energy involves a mass change. So since it involves a mass change, it therefore must use E is equals to delta mc squared, where your E is actually your binding energy. Okay, that's what you want to do now. All right, so here you first need to find out your BE first. You get your mass defect. Your mass defect, as I mentioned to you, delta M is actually the mass difference between nucleus and total nucleons. Okay, so you find the mass difference there, which you can do based on what you have from the table above. You already have the mass of the nucleus itself at 138.955 U. You also have the specific masses of neutron and proton at 1.00863 and 1.00728 respectively. So you just add them all up together. Okay, so here the 57 times 1.00728 U is actually the masses of your protons. The 82 times 1.00863 U is actually the mass of your neutrons. Together, this one is your total mass of your nucleons. Okay, and then the last one here is actually the mass of your nucleus. Okay, now when you write your workings, you actually don't need to write the U inside. You can just write your U at the end of your final answer. That's how the marking scheme usually writes it. It's just that in my case, whenever I did my nuclear physics, I had a tendency to write U inside every time. But if let's just say you want to make your workings a bit shorter, you don't need to write U every single time. You can actually just write the U at the end of your working. Okay. Yeah, and also one thing I should probably mention to you here is this. If your table has already given your masses to a large number of SF, please use the SF as it is. Don't round it up. Okay, don't round out your SF. Don't round up SF during the workings. Maintain as is. Okay, so you really want to round up, only round up to 2 or 3 SF for final answer. Okay, this is generally what we do for nuclear physics. Do not round up the SF during your workings, only round it out for your final answer. Okay, so after you've done all your calculations, you eventually get your mass defect as 1.6762 U. Okay, then from there you want to find the binding energy, right? So here, if you look at the first part of your question, you already found out that if you have a mass defect of 1 U, it gives you 934 mega eV. So what about 1.16762 U? You just take that 1.6762U multiply with 934. That's what you're doing right over here. Okay. So this entire thing here, okay, maybe I better just circle it out. This one here is actually your BE only. Okay. If you want to find BE per nucleon, you take BE, binding energy, divide by nucleon number. Okay. The blue colored numbers that I just, the blue circle here is representing BE. The red circle here is representing your nucleon number. Okay, that's how you got your BE per nucleon here in the first place. Okay, so your answer will be 7.85 mega EV. All right, now this is your final answer. This is where you actually run out your answer to 2 or 3 SF. Okay, you don't need to write it all the way up to like 6 or 7 SF here for final answer. Okay, so this is binding energy per nucleon 7.85. Then after that, you go on to the next page. So if you're okay with this, I'll just clear off everything. Now in part C, they mentioned this. State and explain whether the binding energy per nucleon of uranium-235 will be greater, equal, or less than your answer in B2. So in your case, just to recap a little on what you just did, the binding energy per nucleon of lanthanum 139, which you just found, was 7.85 mega EV. It's 7.85 mega EV. Okay, maybe I use a different color here. 7.85 mega EV. Now here they want you to find out or comment on the binding energy per nucleon of uranium-235. Would it be greater, equal to, or less than? Okay. So here, there's actually an answer that the marking scheme used. That one is actually in red here. This is the actual marking scheme answer. So it's probably better if I just explain from there first. So this question is worth 3 marks. The marking scheme worded the answer as this. They first mentioned that when nucleon number is above 56, binding energy per nucleon decreases as nucleon number increases. And then subsequently, uranium-235 has a larger nucleon number than lanthanum-139. Thus, uranium-235 has less binding energy per nucleon. Okay, so if you just read it as it is, it kind of doesn't really make sense. You have to relate this answer to your binding energy curve. Only then would your answer here make sense. You see, I asked you to remember the binding energy curve shape, right? And the value that corresponds to the peak. So the general shape was like this. And you have 56 right over here for the peak, isn't it? So your nucleon number is 56. Above 56, obviously your nucleon number would increase. And then after that, you see that if you're talking about uranium-235, uranium-235 is probably here. Uranium-235 is probably here. And then lanthanum-139 is probably here. Okay, so uranium-235 having a larger nucleon number than lanthanum-139, this corresponds to uranium-235 having a lower binding energy per nucleon compared to lanthanum. Okay, so this answer only makes sense if you relate it to your binding energy curve. Okay, so that's the answer from the marking scheme. Now there's another answer that I use. This one, is the one that I written in pencil here. Okay, so remember just now I told you that the goal of any nuclear reaction the goal of any nuclear reaction is to become more stable. Okay, the goal of any nuclear reaction is always to become more stable. So you look at the nuclear reaction that you've had from before, which is this one. Okay, wait, let me just get it back. If you look at the nuclear reaction that you had from before, which is this one, uranium plus with neutron gives you molybdenum, lanthanum, neutron, electron, and energy, right? Isn't it? So before your reaction, which is this one is considered to be less stable. But then after your reaction has occurred, this one is already considered to be more stable now. Okay, so going from here to here, you become more stable. Okay, this one is you become more stable. All right, and also I mentioned to you that Be per nucleon is a measure of stability. Okay, it's a measure of stability. So the higher, this one is, if I say Be per nucleon is higher, that means it is more stable. Okay, so right now the question is asking you to make a comparison between uranium and lanthanum here, you see. So lanthanum, I know definitely is going to be more stable than uranium. So its Be per nucleon definitely will be higher. Okay, or I can look at it the other way around, the converse. Uranium-235 is actually less stable. Therefore, you have lower Be per nucleon. Okay, that's one way of looking at it, how you can actually determine whether it is going to be less. Because the answer that I wrote was something like this. I'm just going to erase it. Sorry, I'm just going to erase some of this stuff here. Sorry. Here I wrote something like this, where I said that lanthanum-139 is more stable than uranium-235 after the nuclear reaction. The more stable a nuclide, the higher the Be per nucleon. Therefore, uranium-235 will have less binding energy per nucleon. This is one way of doing it. Okay, but this isn't the official marking scheme answer. The official marking scheme answer is the one below here. Okay, so that is for that particular part. Have a look at page 18. All right. Now in page 18, they mentioned this for you. Our possible nuclear reaction that takes place in a nuclear reactor is given by this following equation here, and data for the nuclei and the particles are given in the table below. Determine for this nuclear reaction the value of x. What should be the value of x here? Now, from doing all these examples, you notice that this equation here just now, the equation that is stated here to you here, is actually that same equation from the previous example in page 20, page 20, sorry. We're in page 18 now. Just now we were at page 20. Right? You look at the equation in page 20, which you just completed. And then you look at the current equation in page 18 that you're doing. They ask you to determine for this nuclear reaction the value of x. This one, if you relate to that one you already know is 7 now. But if let's say you want to write out the workings, you're basically applying conservation of your proton number. Okay, so if you use conservation of proton number, this one will actually be 92 plus with 0 equals to 42 plus 57 plus 0 plus negative x. Wait, sorry. Plus with, oh, sorry, my mistake. Plus with x negative 1. Okay, So you try to solve this. X is therefore going to be 7. You get the answer as 7. Okay. This is you applying conservation of proton number. Okay. So this is just worth 1 mark. And then after that, for part B1, they ask you to show that the energy equivalent to 1 U is 934 mega eV. Again, this is something similar to what we've just done in page 20. So let me just open it up for you. So it's going to be the last question again, if I'm not mistaken. Yeah. So in your case, you do back the exact same working as before, where you say that E is equals to delta mc squared, the mass defect is U, sub in the value of U, sub in the value of speed of light, square it, you get this value in joules. Then from that value in joules, you change it to EV by dividing 1.6 times 10 power minus 19. Then change it to mega EV. All right, it's the exact same working for 3 marks. Okay, so that's all right. Now here is where you will do the question a bit differently. If you look at page 20, what they asked you was to find binding energy per nucleon of lanthanum. Then you use E equals to delta mc squared. In page 18, this one, they ask you to calculate the energy in mega EVs released in this reaction. Not asking you binding energy, all right? They're asking you the energy released in your reaction. Give your answers to 3 significant figures, okay? So in your case, if you look at your reaction here, maybe it's better if I just rewrite the reaction. Just give me a moment to write out the reaction. I'll copy out the reaction for you. In your case, you had uranium-23592 plus neutron-10, giving you molybdenum 9542 plus lanthanum-139 over 57 plus 2 neutron-01 plus 7 electrons. Just give me a moment. This is plus 2 neutron-01 plus 7 electron -10. Okay. So in your case, you want to find the energy release. Now, in your case, you have reactants and product. When it comes to energy release during a reaction, what you look at isn't the nucleus and the nucleons anymore. What you look at is actually the reactants and products. If I'm talking to you about reactants is this one. These are your reactants. But if I'm talking to you about your products, these are your products. Okay. Now, same thing occurs, same thing here like before. You are undergoing a nuclear reaction. Your reactants are actually less stable. Your products is actually more stable. Okay, going from reactants to products, you're actually trying to become more stable. And then when you go from here to here, you actually have a mass defect. You have mass changes that are occurring between your reactants and products. So because there's a mass change and there's energy release here, the equation to use would be E equals to delta mc squared. Because in general, this one, as I mentioned to you, is to find energy associated with mass changes. To find energy associated with mass changes, okay? Which in your case, it could have been used for 2 specific things. We already did the first example. This one was to find BE of a nucleus. In our current example, we want to find energy release in a nuclear reaction. Okay, so if you try to recall what we just did last example in page 20, we were actually trying to find the BE of your lanthanum. This one use E equals to delta MC squared. And then now, in our current example, for this entire thing, we are also using E is equal to delta MC squared. Okay, so that's the thing I want to stress to you now. It can be used for two different things. Okay, depending on your question context. So right now, if you want to find out the energy in mega EV released in your current reaction, first find out your mass defect again. Okay, but your mass defect now will be the difference in mass between your reactants and products now. Okay, not the difference in mass between a nucleus and these individual neutrons. That one is a different thing. That is only for binding energy. Okay, so here you have already been given all the masses: uranium, molybdenum, lanthanum, neutron, and electron. So all you just need to do is you just sub in all the values accordingly. All right, so this is your working now. Delta M is mass of reactor minus F mass of your product. So whatever you have here, 235.123 plus 1.00863, this is actually the mass of your reactant. This one is over here. Okay, maybe it's better just do it like this. This is the mass of your reactant actually. Give me a moment to highlight it. This is the mass of your reactant. And then the rest of this is actually the mass of your product. Okay, so eventually you will get the answer 0.210527. Okay, and don't forget to add your 2 and 7 inside your equation, all right, because you have 2 neutrons and 7 electrons there. Okay, now also I did mention to you, you don't really need to write U in your working, you just need to write the U at the end of your workings. Okay, because if you try to write U, you notice that you tend to have to use a lot of brackets, square bracket, round brackets, and whatnot. So to make your life easier, just don't bother to write the U now. Only write your U at the end of your working. Okay, and another thing I also should probably mention, because this is something that people have asked, should it be mass of reactant minus mass of product, or should it be mass of product minus mass of reactant? Okay, now in my case, I actually already know that with some foresight, this one is actually heavier. This one is actually lighter, because energy is released. Energy is released here, so I have some masses that has been lost already. So whatever I get at the end will be lighter. That's why here when I take the mass of the reactor minus the mass of the product, I will get a positive value. Okay, this is what you notice I tend to use. If you use it the other way around, where you take mass of products minus mass of reactant, you will get back that same magnitude, just that maybe you get a negative answer to your value. Okay, so don't bother so much about that lah. If you're concerned about whether should it be mass or reactant minus mass of product, and somehow you have some difficulty in recalling which one should be which, just don't bother. Take either one, just modulus it. Okay, you can choose either one, mass reactant minus mass product minus mass reactant. If you really do not want the negative to be in the way, just modulus the whole equation, then the issue will be solved. Okay, this is just something for you to think about lah, if you're just concerned about the negative sign there. All right, so your mass defect is 0.210527 U. You want to find the energy here. Same thing as before already. Just now you already found out that 1 U is 934 mega EV. You're trying to find out how much is 0.210527 U. Okay, how much is it? You just take your mass defect, multiply with 934, you're going to get the answer as 197 mega EV. Okay, just like that. So this is all right. Then we move on to part C. Now in part C, what they mentioned is this: suggest the forms of energy into which your energy calculated in B2 is transformed. What are the forms of energy that your energy release has been converted into? Okay, so you can actually say that this is worth 2 marks. You can actually say that the energy release has actually been converted into kinetic energy of your products, which is basically this. These products here have KE because after your reaction, they will be moving about. So they move about, they have speed, they have KE. Okay, so you can say that for one, your energy release has been converted into kinetic energy of your products and also into your gamma ray photon energy. This is the other mark. Okay, the term photon is something that you guys learn in quantum physics. So in Charterhouse, you guys already went through quantum, I believe. So you know that EM radiation can be thought of as a photon, which is actually a packet of energy of electromagnetic radiation. So these are the two answers. Okay, actually your reaction here, you also have emission of gamma rays. It's just that it's not written here. So here you actually have also plus gamma rays. So you have kinetic energy of your products and also gamma ray photons. Okay, these are where your energies got converted into. All right. Now, if you say is thermal or light energy as your answer, this is actually not accepted. Okay, because there's a more specific term for it. Light energy here refers to EM radiation, right? Sorry, light energy here refers to EM wave. EM wave is photon, isn't it? So it's more accurate to say it's photon energy. And then thermal energy actually comes from kinetic energy, right? Because if you went through ideal gases, remember it was mentioned to you, mean kinetic energy is 3/2 kT. So thermal temperature is related to kinetic energy. So rather than saying thermal energy, it's more appropriate to say kinetic energy. Okay, you're just trying to use a more precise term, in other words. Okay, so that's for this particular question. Next one that I want to do with you is page 40. Okay, you will notice that these 3 pages, the equations that have been given to you are actually the same. Okay, there's some differences here I want you to be able to see. Okay, so you look at page 40, November 2019 P41, they again tell you a possible nuclear reaction that takes place is this one, which is actually the same equation in page 20 and page 18. All right, but the only difference now is that they didn't ask you to find out the number of electrons involved. And then from here, they mentioned to you that data for the nuclei in the reaction are given in this table here. And from there, show that the energy equivalent to a mass of 1 U is 934 mega eV. This one we've already done it twice already, so probably there's no need for me to go and explain this. You're just going to use E equals to delta MC square. So let me open up the past here first. This is November 19 P41. Okay, last part again. Okay, so you still use E equals to delta MC square, follow the same working as you did in the last 2 questions, you'll be able to get the answer. Okay, so this one not a big issue. Now then from here, if you look at B1, use the data from figure 12.1 to calculate the binding energy per nucleon of a nucleus of uranium-235, and then complete figure 12.1. Okay, here they want you to find the binding energy per nucleon of uranium-235. Okay, so uranium-235 is this thing here. So in your case, if you wanted to find the binding energy per nucleon, one of the things I did mention to you is that binding energy per nucleon from before. Let me just write this. Your BE per nucleon is actually just BE over nucleon number. Okay, so in your case, you have uranium-235. Uranium-235, you want to find the binding energy. If you want to kind of visualize it again, uranium-235 92 has 92 protons plus with 143 neutrons. Okay, so over here 92 protons and then 143 neutrons. You're supposed to split it out into a number of particles, a number of individual nucleons here like this. So you're supposed to get 92 protons and then 143 neutrons. Okay, right? So this is going from your nucleus to your nucleons. All right. So here I mentioned to you, you would have a mass defect again from nucleus to your nucleons. That energy caused by your mass defect is your binding energy. So in your case, you are really just supposed to find the mass defect between your nucleus and your nucleons. Here, they've actually made your life simpler. They've already told you the mass of your nucleus. This one is the mass of your nucleus. And then they already told you the total mass of your separate nucleons. So this one is sum of the masses of your nucleons. All right. So you take the difference between those two. This one is already your mass defect. Okay. So now you want to find your binding energy. You just use mass defect times the energy equivalent to 1U. Take 1.865 times 934. You're going to get 1741.91 mega eV. Then subsequently, to find binding energy per nucleon, just take BA divided by your nucleon number. You will get the answer is 7.41 mega eV. All right. So use this to complete your table. You will get this. All right. Now, how do I know that I need to write it in terms of 3dp? It's because you see this one is 3dp. You obviously need to write this as 3dp also. Okay, I know my answer here is just 2dp at 3SF lah. But when you go and fill in your table, you ideally should maintain the same dp. All right. Okay, then part 2. Part 2 is referring to this one. Now, for part 2, they mention this. The nucleon number of an isotope or element Rutherfordium is 267. State whether binding energy per nucleon of this isotope is greater, equal, or less than binding energy per nucleon of uranium-235. So we kind of did a question similar to this just now, just that this time we don't really have to explain why. So your B per nucleon graph, you recall it is actually this one, right? So the peak will always belong to 56. If you're talking about Rutherfordium is 267, the nucleon number, but uranium is 235, you could probably say that uranium-235 is here. This is uranium. Then Rutherfordium is probably somewhere here because it is 267, you see. So this is Rutherfordium. I do not know what is the symbol for Rutherfordium. Let's just call it as R. You'll be able to see that the binding energy per nucleon of Rutherfordium is actually lesser. So answer is just lesser. Okay, so far so good with this. Right, now here you look at this particular question. They are asking you to calculate the total energy in mega EV of energy released in this nuclear reaction. Okay, so notice that this question here is actually the same as what you did in page 18. Okay, this question in page 40, notice that they were talking about the same nuclear reaction as in page 18, which was this one. Now let me just go that. It was talking about the same nuclear reaction. The nuclear reaction in page 18 is this. The nuclear reaction in page 40 is also the same reaction. It's the exact same thing. And notice that they're also asking you the exact same question too. Same exact equation, but same and also same exact question. So in page 18, they ask you find out the energy released in this reaction. This one you use E is equals to delta mc squared. Okay, page 18, this one was E is equals to delta mc squared. Okay, this one was E equals to delta mc squared for the energy release in the reaction. Okay, so for page 40 now, it's the same exact equation. It's also the same exact question. But why is it that in my current case, if you look at the workings later on, I'm actually not using E is equals to delta mc squared. I'm using something totally different instead. Okay, sorry, I cannot delete this. But in my case here, for page 40, for energy released in a nuclear reaction, I actually did not use E equals to delta mc squared. Instead, I avoided using it. Now, what's the reason for that in the first place? The reason for that is because you do not have the exact same, you do not have the masses of everything. You see, in your current question, one of the things that you did to find the energy release just now was that you find the masses of your reactants, and then you find the masses of your products, like this. And then after that, you find the mass defect between them, so that you can use E is equals to delta mc squared, right? This was what you did in page 18. You found out the masses for reactants and products, then you use E equals to delta mc squared. Now, if you had tried to use it for page 14 now, your current question, you cannot do this because you have certain values that are missing. Let's just say that I ask you to look at your current equation now. You know the exact mass of molybdenum. You do not know the exact mass of neutron. Notice that there's no mass of neutron listed here. The molybdenum mass is also listed to be an exact value. Lanthanum mass is also listed to be an exact value. And then neutron again is unknown. Electron is again unknown. Okay. Now for neutron, mass of neutron, you cannot just simply say it's 1U. This one I mentioned to you at the beginning of the lesson. When you say mass of proton and mass of neutron is equals to 1U, that was more for particle physics in AS, where you're just working to up to 2 or 3 SF. That time is correct to say it's 1U. But in your current chapter, particle physics, because you're dealing with atomic masses whose differences are really, really, really small, you need to work to a larger number of SF. So you just saying that mass of neutron here is assumed to be 1U is actually the wrong assumption. Okay, because I've had people assume that, oh, neutron is just 1U. Then I can find the mass of the reactants and product properly. No, that is not the case here. So you see, you do not have the mass of your neutron, neither do you have the mass of your electron. Therefore, you can just say this just now. Mass of neutron and electron are unknown. Therefore, mass defect cannot be found accurately. That's why you cannot use E equals to delta mc squared. If you want to make a comparison with page 18 just now, page 18, you look at your table, they did actually give you the mass of your neutron and electron. That's the reason why you could use E equals to delta MC squared there. But in page 40, no, you cannot do so. Okay, that's just the background of this, why you cannot even use E equals to delta MC squared. So if that one is okay, then I go on to explain something else from there. Okay, under page 6 of your notes. Okay, so let me just try to explain this properly without rushing. Now, if you want to find energy change in a nuclear reaction, there's another way you can do so. That one is by using another separate equation. So like this one here, just now I told you to find energy release in a nuclear reaction, you could have used E equals to delta MC squared, right? There is actually another different way you can find energy release in a nuclear reaction. This one is actually using or E is equals to BE of your products minus BE of your reactants. Okay, to find energy release in a nuclear reaction, you actually can use another separate equation, which is this one. Energy of products minus energy of your reaction. Okay, so why do you even say that? It will probably make more sense to look at it in the form of an energy level diagram. Okay, so let's just go through the point one by one slowly first. Now, one of the things that you will remember me saying earlier just now is that in any nuclear reaction, the goal is always to become more stable, going from reactants to products, right? Okay, now a higher stability generally means a lower energy level. Okay, this one I'm not talking about binding energy. I'm just talking about energy levels. Okay, something like energy levels of electrons in chemistry. All right, you have something at the higher stability, it will be at a lower energy level. Just like in chemistry, we say that if an electron is at a lower energy level, it is more stable. So I'm applying that same concept for a nucleus right now. Okay, so if higher stability means lower energy level, this would mean that going from reactants to products, your energy level generally decreases. Okay, so in my case, if going from reactants to products, my energy level decreases, this would mean that the total binding energy of products is greater than the total binding energy of the reactants. So energy is released in this reaction. So to find energy released during a nuclear reaction is actually B of products minus B of reactants, which is what you see here. Okay, to give you a better idea of what all this actually means, you just look at the diagram below. This one. Let's just consider this as your energy level diagram. You draw 3 lines. This first line here represents the energy level at infinity. Okay, and there will be 2 additional lines. This green line here and this blue colored line here. Okay, now because I mentioned to you that your nuclear reaction is trying to become more stable from reactants to product, that would mean that energy level would decrease. So here, this one would be at your representing the energy level of your reactants. This one is higher E level. Okay, and then this one would be representing your products, the blue colored line. This one is at lower E level. Okay, in my case, higher E level means less stable, but lower E level means more stable. Okay, so when I go from reactants to products, I'm actually jumping from this higher energy level to this lower energy level here. Okay, that's what you can see. All right, let me just draw some random line here for you to see. Maybe it's in black. Okay, from reactant, I go down to products, from less stable to more stable. Okay, and then now if I look at it in another different way, if I try to relate my energy level diagram to BE, you remember that BE is the energy required to separate a nucleus into individual nucleons completely to infinity, right? So let's just say that you try to modify the definition a little to represent BE of reactants and BE of products. BE of reactants would be the energy required to separate all your reactants into individual nucleons. BE or your products will be the energy required to separate all your products into individual nucleons. So in the case here, BE of reactants is this line. You're going from this line here to this line because you're separating your reactants into individual nucleons to infinity. So that arrow that you see here, the orange colored arrow going up, is representing BE of your reactants. Now, if you apply that same concept for BE of your products, you're trying to separate your products into individual nucleons completely to infinity. So the energy required is this one. Again, this is the BE of your products. It's the blue colored line there. So notice that there's actually a difference in the line, in the length of the lines. The difference in the length of the lines represents to you a difference in the energy involved. Okay, so the difference in energy involved here is actually your energy release, this one. Okay, I know here energy will be released because I'm going from higher energy level to lower energy level. Okay, now since you guys have gone through quantum physics before this in school, you probably would know what I'm talking about, because you see, if you remember what you learned in quantum physics, you guys have learned emission and absorption spectra. Have you guys learned emission and absorption spectra? You probably would have learned something about electrons jumping from higher energy level to lower energy level, right? So if you guys were talking about emission absorption spectra in quantum physics, if I say for you that your electron went from here, lower energy level, to a higher energy level, from here to here, this one, what you would have learned is that your electron must absorb energy from photons. Okay, so your direction going up here is going to absorb energy. But similarly, if you have an electron from a higher E jumping down to a lower E, what we will mention here is that rather than you absorbing a photon, absorbing energy from photon, you are releasing energy in the form of photons. Okay, so that is something that you guys would have learned under quantum physics. Something jumping to a higher energy level would absorb energy. Something jumping to a lower energy level would release energy. So in your case, notice that from reactants to products, you're actually jumping from higher energy level to lower energy level. That would mean that you must be releasing energy here. Okay, so if you want to find the magnitude of the energy release, you need to find the difference in the binding energies of the products and reactants. That's why here, when I ask you to find the energy release in the nuclear reaction, I mentioned that you can actually use this particular equation instead. Okay, so you apply this concept to your current question from before, the one in page 40. This is the reason why you're doing this now, no? In terms of your working. So let me just erase certain unnecessary stuff. So here, calculate the total energy in mega EV released in this nuclear reaction. That is the reason now why you are using BE of products minus BE of reactants. Because here, although you do not know the masses of all the particles, you know the masses of your products and reactants. Okay, so in your case here, let me just make some mental, let me just go and mention this to you. Now, you want to find the BE of your products here, so BE of your reactants here, and you want to find the BE of your products here. Okay, so to find your BE, notice that you can find it from your table. You see, you're given the a table showing BE per nucleon. So BE would just be BE per nucleon multiplied with nucleon number. Okay, multiplying with nucleon number. Okay, so you have B per nucleon as well as the respective nucleon numbers for each of these elements. You can actually find out the respective BE. Okay, now another thing I should probably mention to you here is this. You are only finding the BEs and summing them out for these particles only. But you will not be finding BEs for neutron as well as electron. Now, why is it that you do not find the BE for neutron and electron? Number one, neutron, okay, maybe I better just split it out like this. Now, neutron is already a nucleon. It is already a nucleon. It cannot be split anymore. Therefore, no BE. Okay, there is no BE for neutron because it's already a nucleon. Definition of BE formally is you are trying to split a nucleus into individual nucleons completely to infinity, right? So because your neutron is already a nucleon, there is no point in splitting it out anymore. It cannot split out anymore. So no BE here. And then a similar reasoning could also apply for electrons. Electron is already the most fundamental particle. It's already a fundamental particle. Same reasoning. It cannot be split further. Therefore, no BE2. Okay. With these two in mind, that's the reason why you don't even bother finding the BE for neutron and electron. You are really only summing up the BEs for these elements here, which are listed in your table. Okay. So then you look at the workings, it will be something like this. This is basically the BE of your products. And then this one is basically the BE of your reactants. So eventually you get 199 mega EV, just like that. All right. So that's for this. So in part D, they ask you something else. Part D is asking you this. The nuclei in 1.2 times 10 power minus 7 mole of uranium-235 all undergo this reaction in a time of 25 milliseconds. Calculate the average power released during the time of 25 milliseconds. Okay, so you consider this now. One nucleus of uranium-235 releases 199 mega EV of energy. That's what you found here. Okay, for the nuclear reaction, one nucleus of uranium-235 will release this amount of energy. Now, in your case, if we tell you that you have 1.27 moles of uranium-235, how many nuclei do you have here? So we would say that 1.2 times 10 power minus 7 moles has 1.2 times 10 power minus 7 times 6.02 times 10 power 23 nuclei. Okay, if you remember, number of moles is number of nuclei divided by your Avogadro constant. So that number of nuclei is number of moles times Avogadro constant. That is what you are kind of doing here. They already told you the number of moles as this amount. 1.2 times 10 power minus 7. You just need to multiply with Avogadro constant to get the number of nuclei. Okay, so this one here is actually the number of nuclei. Okay, So if then you want to find total energy release, from there, total energy release will be your number of nuclei multiplied with energy release for one nucleus. So we know one nucleus release this amount of energy, and we have this amount of nuclei now. You basically take this, multiply with this, okay? Because now we want to find power. Power, we know, is total energy release over total time, right? So before we can find the total energy release, you need to find the number of nuclei, multiply with the energy release for one reaction, so for one nucleus, that gives you total energy release. This is what you're going to get, okay? This one is number of reactions or number of nuclei, okay? 1.2 times 10 power minus 7 times 6.02 times 10 power 23, giving you this. So get the energy release, divide by your total time of 25 milliseconds. You will get this answer, 9.2 times 10 power 7 watts, okay? Remember to change your milliseconds to seconds.